Welcome. In this session, we will explore the problem number 2217 titled Find Palindrome with Fixed Length. We'll break down the problem, analyze the approaches considered, and work towards an effective solution. Let's dive right in. The problem we're tackling involves finding a specific palindrome with a fixed length. You are given two integers, k and n. Here, k represents the number of digits in the palindrome, and n is the one-based index of the palindrome you need to find. The goal is to return the nth smallest palindrome with exactly k digits as a string. If such a palindrome doesn't exist, you return an empty string. Now, a palindrome is a number that reads the same forward and backward, like 121 or 3443. On the other hand, numbers like 123 or 1234 are not palindromes since they differ when reversed. You are guaranteed that k will range between 1 and 15, and n can go up to 100,000. This ensures that the palindromes can be quite large, so efficiency is key. The output must always be a string, even if the palindrome is numeric. To clarify the problem, let's look at some examples. First, consider k equals 2 and n equals 3. The task is to find the third smallest two-digit palindrome. The two-digit palindromes, in ascending order, are 11, 22, 33, 44, and so on. Here, the third palindrome is 22, so the output is the string 22. In another example, where k equals 3 and n equals 5, we need to find the fifth smallest three-digit palindrome. The three-digit palindromes are 101, 111, 121, 131, 141, and so on. The fifth palindrome in this sequence is 141, so the output is the string 141. These examples help illustrate how the palindromes are ordered and how to determine the nth one. Now let's examine a few more examples to deepen our understanding. When k equals 4 and n equals 12, we need the 12th smallest four-digit palindrome. The sequence begins with 1001, 1111, 1221, 1331, and so on. If we continue this pattern, the 12th palindrome in this list is 4004, so the output is the string 4004. On the other hand, for k equals 1 and n equals 10, we are tasked with finding the 10th smallest one-digit palindrome. The one-digit palindromes are just the numbers 1 through 9. Since there is no 10th one-digit palindrome, the function returns an empty string. These examples highlight scenarios where the output is either a valid palindrome or an empty string if no such palindrome exists. The constraints and edge cases are critical for understanding the problem. First, k ranges from 1 to 15, and n can go up to 100,000. This means the solution must handle both small and extremely large inputs efficiently. For edge cases, consider when both k and n are at their smallest values. For example, with k equals 1 and n equals 1, the output should be 1 since it's the smallest one-digit palindrome. However, if k equals 1 and n equals 10, the output is an empty string because there are only 9 one-digit palindromes. Another edge case arises when n exceeds the total number of palindromes for a given k. For instance, with k equals 4 and a very large n, the function should return an empty string. It's also important to handle both odd and even values of k correctly, as this affects the symmetry of the palindrome. Palindromes are symmetrical by nature, which means the first half of the digits determine the second half. This property is key to generating palindromes efficiently. For a given k, the total number of palindromes can be calculated as 9 *10 k1 //2. This formula gives the count of palindromes with k digits, so we can quickly determine if n exceeds this count and return an empty string when necessary. By leveraging symmetry and limiting calculations to the first half of the palindrome, we can generate the required palindrome without iterating through all possibilities. This approach ensures the solution is both efficient and scalable, even for large values of k and n. To start, let's explore the brute force approach. The intuition here is straightforward: generate all possible numbers with exactly k digits, check each one to see if it's a palindrome, and keep track of the palindromes until we find the nth one. The steps involve iterating over all numbers in the range of 10 k1 to 10 k1, since this range contains all k-digit numbers. For each number, we convert it to a string and compare it to its reverse to determine if it's a palindrome. If it is, we increment our count until we reach the desired n. However, the inefficiency of this method becomes apparent when we analyze its complexity. Generating and checking all k-digit numbers leads to a time complexity of 10 to the power of k asterisk k, which grows exponentially with k. Additionally, the space complexity is k due to the string operations involved. While this method is conceptually simple, it's impractical for large values of k because it doesn't take advantage of the inherent structure of palindromes. This results in wasted computations, making it unsuitable for our needs. Now, let's consider the optimized approach, which directly constructs palindromes without iterating through all k-digit numbers. The key intuition is that a palindrome's symmetry allows us to determine the entire number based on just its first half, known as the prefix. For even values of k, the prefix completely defines the palindrome, while for odd values of k, the middle digit is part of the prefix. By focusing on the range of possible prefixes, we can calculate palindromes much more efficiently. For example, if k is 5, the prefix ranges from 100 to 999. Using this range, we can directly compute the nth palindrome by identifying the corresponding prefix, reversing it, and appending the reversed portion to construct the full number. This avoids unnecessary computations and allows us to handle very large values of k or n. The process involves determining the range of prefixes, checking if n fits within the total number of palindromes, and then constructing the desired number mathematically. This streamlined method leverages the properties of palindromes for efficient computation. The complexity of the optimized approach is much more favorable compared to the brute force method. Constructing a palindrome involves k time, as the steps include simple string operations like reversing and concatenation, and the space complexity remains k as well. We chose this strategy because it efficiently computes only the required palindrome, without generating unnecessary numbers or performing redundant checks. Its scalability makes it ideal for cases where k or n is large, and it avoids the exponential growth in computations seen in the brute force approach. While there's a slight increase in complexity due to handling odd and even cases separately, this trade-off is minimal when compared to the significant gains in performance. Overall, by directly leveraging the symmetry of palindromes, this approach provides an optimal solution that aligns well with the problem constraints and ensures efficiency even for larger inputs. To tackle this problem, we need to find the nth smallest palindrome number that has exactly k digits. To start, let's understand how palindromes work and how we can navigate the range of k-digit numbers. Any number with exactly k digits starts at 10 raised to the power of k-1, which gives us the smallest k-digit number. For example, with k equal to 3, the range starts at 100. Similarly, the largest k-digit number is 10 raised to the power of k-1, in this case, 999 for k equals 3. A palindrome is a number that reads the same forwards and backwards, such as 121 or 131. One straightforward way to solve this problem is through a brute force approach. Here, we iterate through all possible k-digit numbers, checking each one to see if it's a palindrome. We keep track of how many palindromes we've found and stop once we reach the nth palindrome. To begin, we initialize the starting point as the smallest k-digit number, the endpoint as the largest, and a counter set to 0 for tracking our progress. Now, to implement this brute force approach, we iterate through all numbers within the range of k-digit numbers. For each number, we convert it to a string so we can easily check if it's a palindrome. This is done by comparing the string with its reversed version. If they match, we know the number is a palindrome. When we find a palindrome, we increment the counter. Once the counter matches n, we return the current number as the nth palindrome. However, we also need to handle edge cases. For example, if n is larger than the total number of k-digit palindromes that exist, we should return an error or handle it appropriately. In terms of complexity, this brute force method involves generating all k-digit numbers, which takes 10 to the power of k time, and checking each number for the palindrome property, which takes k, for string operations. This results in a total time complexity of 10 to the power of k asterisk k. The space complexity is relatively low, requiring k, for temporary string storage during the palindrome check. While the brute force approach is simple, it's not efficient for larger values of k. To optimize, we can leverage key properties of palindromes. One crucial insight is that palindromes are symmetric, so instead of checking the entire number, we only need to focus on the first half. By mirroring the first half, we can construct the entire number and immediately verify its palindrome property. This symmetry allows us to generate k-digit palindromes directly, skipping over non-palindromic numbers entirely. Brute force is limited because it unnecessarily processes numbers that could never be palindromes, leading to inefficiencies. By focusing only on valid palindromes, we can significantly reduce the search space. This optimization is particularly beneficial for large values of k, where the range of numbers grows exponentially. To better understand how the brute force approach works step by step, let's walk through an example. Suppose we're given k equal to 3 and n equal to 5. This means we need to find the fifth smallest palindrome with 3 digits. We start at 100, the smallest 3-digit number, and check each number sequentially. The first number, 100, is not a palindrome. The next, 101, is a palindrome, so we increment our counter to 1. We continue checking, 102 is not a palindrome, but 111 is, so we increment the counter to 2. Repeating this process, we keep finding palindromes and tracking the count until we reach the fifth, which is 131. This illustrates how the brute force method systematically examines each number, though it also highlights how inefficient this can be as the range of numbers grows. Finally, let's consider an edge case. If k equals 1 and n equals 100, we run into a problem because there are only 9 palindromes with 1 digit, the numbers 1 through 9. Since n exceeds this limit, we should return an error or handle it as an out-of-bounds case. To summarize, the brute force approach is thorough but inefficient for larger values of k and n due to the exponential growth of the number range. Optimizations, such as directly generating palindromes by mirroring the first half, can drastically reduce computation time. These strategies allow us to handle larger inputs effectively, making the solution far more scalable and efficient. Here, we define the kth palindrome method within the solution class. The goal is to compute the kth smallest palindrome of a given fixed length. First, we calculate half_start, which determines the starting point for the first half of the palindrome. This is done by raising 10 to the power of half the integer length, adjusted for whether the length is odd or even. Next, we initialize an empty list called result to store the final answers. Then, for each query in the queries list, we compute the half number of the kth palindrome by adding the query index -1 to half_start. The half number is converted to a string for further processing. To construct the full palindrome, we check if the given length is even or odd. If it's even, the second half is simply the reverse of the first half. For odd lengths, we exclude the middle digit when reversing to avoid duplication. Finally, we check if the resulting palindrome exceeds the specified length. If it does, we append -1 to the result list, otherwise, we convert the palindrome string back to an integer and append it to the result list. At the end of the method, we return the result list, which contains the kth smallest palindromes for all queries. This ensures that the output is ready for any input specifications, including cases where the desired palindrome is invalid due to exceeding the length limit. Here, we begin by importing the necessary libraries and defining the solution class. The primary method, kth palindrome, takes 2 parameters, an array of queries and an integer representing the length of the palindromes we want to construct. To start, we calculate half_start, which marks the starting point for generating the first half of the palindromes. This is determined using the formula 10 raised to the power of, in length 1, divided by 2, which helps us identify the smallest number that can form the first half of the palindrome. Next, we initialize a result array to store the final palindromes corresponding to each query. The loop iterates through the queries array, and for each query, we calculate half number, the numeric value of the first half of the palindrome, by adding the query value to half_start and subtracting 1. We then convert this number to a string, half_str, which allows us to construct the full palindrome. Depending on whether int length is even or odd, we concatenate half_str with its reverse. For even lengths, we directly append the reverse, while for odd lengths, we exclude the first character of the reverse string to avoid duplicating the middle character. Finally, we include a check to ensure the length of the constructed palindrome does not exceed int length. If the computed palindrome is longer than the specified int length, we assign -1 to the corresponding index in the result array, indicating that no valid palindrome exists for that query. Otherwise, we parse the palindrome string back into a long and store it in the result array. Once all queries have been processed, the method returns the result array, containing either the palindromes or -1 for queries where the desired palindrome could not be constructed. This implementation efficiently handles the generation of palindromes by focusing on constructing the first half and mirroring it appropriately, ensuring correctness and adherence to constraints. To solve the problem, we start by breaking it into smaller steps. In this example, the queries are 1, 2, 3, and the length of the palindrome is 3. First, we calculate half_start, which determines the starting point for the first half of the palindrome. Since the length is 3, the first half has 3 to 1 // 2 plus 1 equals 2 digits, giving us half_start equals 10 to the power of 1 equals 10. Now, for each query, we calculate the corresponding number for the first half, construct the palindrome, and ensure it matches the required length. For query 1, we compute half_number equals 10 plus 1 equals 10, convert it to a string, and construct the palindrome by appending the reverse of half_str excluding the last character. This gives us palindrome equals 10 plus 1 equals 101. As its length matches the requirement, we add it to the result list. Similarly, for query 2, half_number equals 10 plus 1 equals 11 gives half_str equals 11, and the palindrome becomes palindrome equals 11 plus 1 equals 111, which is also added to the results. Processing query 3, we calculate half_number equals 10 plus 1 equals 12, resulting in half_str equals 12. The palindrome is formed as palindrome equals 12 plus 1 equals 121. Since it meets the length requirement, we append it to the result list. After processing all queries, the final output is 101, 111, 121. Each palindrome is constructed by carefully combining the first half and its reversed counterpart, ensuring it adheres to the specified length of 3 digits. In this second example, the queries are 1, 5, and the palindrome length is 4. The calculation of half_start follows the same approach, but since the length is even, the first half has 4 // 2 equals 2 digits, giving half_start equals 10 to the power of 1 equals 10. For query 1, we compute half_number equals 10 plus 1 equals 10 and convert it to half_str equals 10. With an even length palindrome, the second half is the complete reverse of the first half. This gives us palindrome equals 10 plus 01 equals 1001, which is added to the result list. For query 5, we calculate half_number equals 10 plus 1 equals 14 and half_str equals 14, resulting in palindrome equals 14 plus 41 equals 1441. After constructing both palindromes, the output is 1001, 1441. In the third example, the query is 1000, and the palindrome length is 3. As before, we calculate half_start equals 10. However, for a 3-digit palindrome, the maximum valid half_number is 99, because anything beyond this would create a number longer than the specified length. For query 1000, we calculate half_number equals 10 plus 1001 equals 1009. Since this exceeds the maximum valid range, we append -1 to the result list to indicate that the query is invalid. The final output for this example is -1. To summarize the key logic, the half_start calculation determines the smallest starting number for the first half of the palindrome based on its length. Each query corresponds to a specific half_number, which is derived by adding the query index to half_start. Palindrome construction depends on the length being even or odd. The second half is derived by reversing the first half, either fully or partially. Finally, we validate that the constructed palindrome meets the required length. If it doesn't, we append -1 to the results. In terms of complexity, the solution processes each query in constant time, leading to a time complexity of O(m), where m is the number of queries. The space complexity is also O(m), as we store the results in a list. The time complexity of the kth palindrome function can be broken down step by step. First, calculating half_start involves raising 10 to the power of a small constant, which is a single operation and takes constant time, or O1. Then, we process each query in the input. For every query, we calculate half_number by adding half_start and the query value minus 1. This addition is also a constant time operation, O1. Next, we convert half_number to a string, which depends on the number of digits in half_number. Since the length of half_number is proportional to the input parameter int_length, this conversion takes O, int_length, time. After that, we reverse this string and concatenate it to construct the full palindrome, which also takes O, int_length, time because the operations involve manipulating strings of up to int_length characters. Finally, checking the palindrome's length and appending it to the result list are simple operations that take constant time, O1. When we consider these steps for all n queries, the total time complexity becomes O, int_length, as the dominant factor is the string operations performed per query. For space complexity, we start by examining the intermediate variables used in the function. Variables like half_start, half_number, half_str, and palindrome require space proportional to the number of digits in the palindrome. Since the palindrome is derived from int_length, these variables take up O, int_length, space in the worst case. The result list, which stores the output for all queries, contributes the most to the space usage. If there are n queries and each result is an integer represented with up to int_length digits, then the result list occupies O, int_length, space. Combining both intermediate variables and the result list, the total space complexity of the function is O, int_length. This ensures efficient memory usage compared to alternatives that might store much larger data structures. To appreciate the efficiency of the optimized approach, let's compare it with a brute force method. In the naive approach, we would generate all numbers of the specified length, test each one to see if it's a palindrome, and then retrieve the kth palindrome for each query. Generating all palindromes for a given int_length involves iterating through numbers up to 10 raised to the power of int_length, giving a time complexity of O, 10 caret, int_length. Querying the results would add another O, n, leading to a total time complexity of O, 10 caret, int_length, plus n. For space, we'd need to store all these palindromes, requiring O, 10 caret, int_length, space. In contrast, the optimized approach only computes the necessary results for each query on the fly, without pre-computing or storing all palindromes. This reduces both time and space complexity to O, int_length, which is significantly better for large values of int_length. In terms of best and worst cases, the time complexity remains O, int_length, because each query is processed independently and the operations do not vary based on the input values. The mathematical justification for the stated complexities lies in the nature of the operations performed. Each query involves string manipulation tasks such as converting an integer to a string, reversing it, and concatenating, all of which scale linearly with the number of digits, or O, int_length. No nested loops or recursive calls are present, so the overall processing for all n queries scales linearly with both n and int_length. This independence between queries ensures that the time complexity is proportional to the product of the number of queries and the length of the palindromes, or O, int_length. Similarly, the space required is dominated by the result list and intermediate variables, which also depend linearly on n and int_length. This direct relationship between the problem parameters and the operations performed confirms the efficiency of the optimized approach. When working with this problem, there are several common mistakes to watch out for. First, failing to handle edge cases for k-digit numbers is a frequent issue. For instance, when k equals 1, single-digit numbers like 1, 2, or 3 should naturally be treated as palindromes, but some implementations overlook this. To address it, ensure your algorithm explicitly accounts for the case where k is 1. Another mistake is relying on inefficient palindrome checks. Many solutions use string reversal, like str, number, ::-1, which can introduce unnecessary overhead, especially for larger numbers. Instead, consider using arithmetic methods to reverse digits, which are often more efficient. Lastly, overlooking constraints on n is a critical error. For example, if n exceeds the total number of k-digit palindromes, your code may run into out-of-bounds errors. To prevent this, Pre-compute the maximum number of k-digit palindromes, such as using the formula 9 times 10 raised to the power of k1/2, and make sure to handle cases where n is too large gracefully. Another common pitfall lies in misinterpreting the structure of palindromes. A classic error is constructing palindromes by appending the reverse of the entire number instead of just the first half. For example, if k is 4 and the first half is 12, the correct palindrome is 1221, not 1212. Ensuring the proper construction of palindromes is key. Additionally, failing to optimize for large inputs can lead to significant performance issues. A brute force approach, which checks all possible candidates, may work for small values of k and n, but it becomes impractical as these values grow. Instead, adopting a constructive approach allows you to directly generate the nth k-digit palindrome without iterating over every candidate, making your solution far more efficient. Understanding the structure of palindromes is crucial in interviews. For even-length palindromes, the first half of the number entirely determines the rest. For odd-length palindromes, the first half, including the middle digit, defines the whole. Leveraging this symmetry allows you to construct palindromes efficiently. Pre-computing the range of possible k-digit palindromes, such as by iterating over the first half's range, can further reduce computation time. Beyond efficiency, clarity and edge case handling are vital. Interviewers often prioritize clean, modular solutions that handle edge cases effectively over overly complex optimizations. Lastly, be prepared to discuss trade-offs between brute force and constructive methods during interviews. Knowing when each approach is appropriate and tailoring your solution to fit input size constraints demonstrates a strong grasp of problem-solving strategies. This problem connects to several related challenges in LeetCode. For instance, LeetCode 5, which searches for the longest palindromic substring within a string, requires identifying patterns within text. Similarly, LeetCode 9 checks whether a number is a palindrome, which aligns closely with the symmetry concepts we've discussed. LeetCode 234 involves palindrome checks within a linked list structure, introducing additional complexity due to the data format. Finally, LeetCode 132 extends the idea of palindromes into dynamic programming, focusing on partitioning a string into the minimum number of palindromic substrings. Exploring these problems can deepen your understanding and prepare you for variations of the palindrome-related challenges. There are multiple approaches to solving this problem, each with its pros and cons. A brute force approach is straightforward and easy to implement, making it a good choice for small values of k and n. However, its 10 to the power of k complexity makes it inefficient for large inputs. A constructive approach, on the other hand, directly generates the nth k-digit palindrome in k time, which is highly efficient. The drawback is that it requires a solid understanding of palindrome structure and careful handling of edge cases. Pre-computing all possible palindromes allows for log n retrieval through binary search, but this method demands significant memory, especially for large k. Lastly, a recursive approach to palindrome construction can be elegant and modular but may introduce recursive overhead, making it less suitable for very large values of k. Choosing the right approach depends on balancing efficiency, clarity, and resource constraints. Great job! We've summarized the key concepts and takeaways from solving this problem. Remember, every challenge is an opportunity to grow your coding skills. Keep practicing, and we'll see you in the next session. Thank you. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!